And thank you all for coming. So I'm going to be presenting on some of the work I did during my PhD thesis today. And the title of my talk is Ultrafast Quantum State Generation and Measurement in Nonlinear Nanophotonics. And so to motivate the title of this talk a bit, I first want to talk about quantum information and why we're interested in using it. So we want to use quantum information because it provides us an advantage that is otherwise unattainable by classical means. There are just some things we can do with quantum information that we can't do with classical information. Now, there are a variety of platforms out there to access this quantum information, and I'm showing you some of them here. But we're going to be focusing on one platform specifically throughout this talk, and that's nonlinear optics. So there are some good reasons for focusing on this platform, and the first reason is that it happens at room temperature. So one of the common themes shared among these other platforms is that they require cryogenic temperatures to operate, and this is to freeze out thermal noise so they can observe quantum effects of interest. Now, when we work with optics, we don't have this problem with thermal noise, and so everything we're doing can happen at room temperature, and so we don't suffer from any of the scalability issues imposed by cryogenic operation. So the other reason we'd like to work with nonlinear optics, and light specifically, is because of the very large bandwidth. So another common theme amongst these other platforms is that they rely on electronics in some way or another to do some sort of state generation or readout. And this ultimately limits them to operating at the bandwidths offered by electronics, which is about 100 gigahertz at maximum. By using light, we can do all of our computation in the optical domain, so we don't have to go back to electronics, and we can access all of the benefits of the broad bandwidths offered by light. And as I'll show in this talk, this will allow us to create devices with clock rates beyond 1 terahertz. Now, if light has all of these advantages, then why isn't everyone using it? Well, there are a few drawbacks. So the first fundamental problem that we face in this platform is the nonlinearity. We have a very low nonlinearity compared to other platforms. And as we'll see throughout the talk, this will constrain us in what kinds of measurements and computations we can do. So the other fundamental problem with nonlinear optics is this thing called dispersion. So you're probably familiar with dispersion. It's what I'm showing here in the bottom right, where when we send in a beam of white light to some optical material that has dispersion, it will spread out into its colors. Now, the reason this is a problem for us is because we need to use pulses to make this thing go fast. The idea is to use pulsed light and to make the pulses shorter and shorter so that we can pack more of them together in the time domain and process more information per unit time. But if we were to send a short pulse into a medium that we would like to use, an optical medium, and it encounters that dispersion, just like these colors are spreading out in space, that pulse will spread out in time. And we're going to lose all of the benefits we gain from using pulsed light. So for the purposes of this talk, the problem I'm going to focus on solving is this issue with dispersion. We're going to figure out how can we build devices with low dispersion such that we can use these ultra-fast pulses and access all of the bandwidth offered by light. Now, we know that light can store quantum information, but we still need a way to manipulate it. And the way we're going to manipulate quantum information is with this device. It's called an optical parametric oscillator, and it's based on this thing called the Chi2 nonlinearity. And so I have a diagram of it here. And since it's an amplifier, we can think of its inputs as the signal and the pump. So the pump is what's going to provide our energy for amplification, and the signal is the thing we're going to amplify. Now, inside these amplifiers, there are two different things that can happen. In the first case, we can take photons or particles of light from the pump, and we can annihilate them and create two signal photons in the process. This will have the effect of amplifying part of the signal. In the second case, we can do the time reverse process, where we annihilate two photons from the signal and create a pump photon. This will end up de-amplifying a different part of the signal. So if we want to visualize the quantum information in our signal at the input, one of the ways we can do it is by plotting something like this, which is a quasi-probability distribution along two variables. In this case, I'm calling them x and p. Sometimes I'll refer to them as quadratures as well. Now, this particular state is what we call the vacuum state. It's what you have when you have no photons, you're just left over with quantum mechanical noise. Now, if we put this vacuum state through this amplification process, what will happen is that one portion of the state will become amplified along this x-axis, and one portion will become de-amplified along this p-axis. And we'll get this squeeze distribution that we call squeeze light. And what I'm showing you in the top right is actually a picture of an OPA implemented with a bulk crystal. But we know that using bulk crystals is not enough, because then we're limited to the dispersion of the material. So we have to find some way to implement this OPA that will give us some control over the dispersion. And so the platform we're going to use is something called thin film lithium niobate. So the reason we want to use lithium niobate is it has this Chi2 effect. And the way we're going to implement these devices on a platform like this. So what I'm showing you here is one of the typical chips we use to make devices. And the way we make the devices is we etch ridge waveguides into this chip. What you're looking at here is about 700 nanometers of lithium niobate. This is a side profile of the chip. And that sits on top of a piece of glass, and that sits on top of a larger piece of silicon. And to make these devices, we etch this little trapezoidal-shaped ridge, and so we create a place for the light to flow. But conveniently, we have some control over the geometry here. We can modify the etch depth, the width, and the height of the thin film. And as it turns out, if we pick the correct geometry, we can create a device with very low dispersion, and that will give us two advantages that I'm showing here. So this is our ultrafast OPA, and I'm plotting it against other devices in terms of its gain bandwidth and its gain per unit length. And we can see that we're winning on gain bandwidth by over 10 terahertz. And actually, the next runner-up is just the bulk version of this process. And it's that bandwidth that's going to allow us to access the speed benefits of propagating light. We can also see that we also have very high gain with this device, over 100 dB per centimeter. And that high gain is what's going to help us later to measure these very weak quantum states. So the other reason we want to use lithium niobate is because it offers other devices as well. While these OPAs I'm describing to you will be the beating heart of this talk, they'll be the things doing the actual information processing, we still need other devices to help us. Things like sources, filters, couplers, lasers, all of which can live on this same platform, and all of which we can integrate alongside our OPA to build these large-scale circuits that can actually do something useful. So throughout the course of this talk, I'm going to be introducing these OPAs in three different contexts. In the first context, we're going to show how we can generate quantum states of interest with these OPAs that have a very short temporal duration, so that we can achieve clock speeds beyond a terahertz. In the second part of the talk, we'll be changing gears slightly, and we'll be showing how these OPAs can also measure quantum information, and we'll show that they can actually distinguish between a single photon and vacuum. In the third part of the talk, we'll be taking a different approach to measurement, where instead of measuring this discrete information of whether or not we have a single photon, we'll be using the output statistics of these amplifiers to fully reconstruct the quantum state at the input, all while operating at these terahertz clock rates. So first up is the biphoton source. And the first question you might ask is, well, why do we need an ultrafast biphoton source in the first place? So most conventional sources are limited by dispersion to about gigahertz in rep rates. And for their most common application, quantum key distribution, this limits key rates to between megahertz and gigahertz. Now, with the dispersion engineering we have used to build this source, we can generate biphotons with just 165 femtoseconds of temporal duration, which translates to a maximum clock speed of 6 terahertz. So the way this generation process works is actually what I showed you earlier. We take this vacuum state and we weakly amplify it inside of an OPA. Now, these plots are just one way to describe the state. And what I've written down here is an equivalent description for the state on the right. It's an equivalent description for squeezed vacuum. And if we look at this state, what it's telling us is that when we try and measure how many photons are there, most time we just get 0. We come up empty-handed. But sometimes we get 2 photons. And these are the biphotons that we actually want. We want to exploit the entanglement of these biphotons to achieve some sort of advantage. Now, we'll also end up getting these multi-photon states like 4, 6, and so on. And we'll show that these are actually a problem for us, and we'll need to come up with some strategy to mitigate them. So to characterize the performance of this source, we use an experiment that looks like this. So we start out on the left here with this mode-locked laser. This will give us a 75 femtosecond pulse every 4 nanoseconds. So we direct that pulse into these 3 pieces of optics, which are going to lower the incoming power to our chip, because we only want to pump with a very small amount of pump light. That light will get focused down onto the waveguide with this objective, and it'll propagate in the waveguide, where hopefully we will generate some biphotons. Now at the output, we're going to collect all of our light with a lens fiber, and then we're going to send everything back into free space. And this is so that we can filter out the pump light, because we're not interested in measuring the pump. We just want to measure the light that we generate inside this OPA. So after that, we do some bandpass filtering to remove higher order spectral modes. And from there, we go to some sort of measurement. And in this case, we're going to do single photon counting measurements. And there are 2 types of measurements we're going to do. They're going to tell us different things. So the first measurement is this experiment. It's called the Hanbury-Brown twist experiment. We just send this light into a 50-50 beam splitter, and half of it goes to one detector, and half of it goes to the other detector. And what this experiment will do is it will tell us the signal to noise ratio of our source, as well as how efficiently we're generating these biphotons. In the second experiment, we'll do something slightly different. We're going to measure something called the heralded G2. Now that's going to be a measurement of how efficiently we can herald single photons. And I'll talk in a few slides about why we want to herald single photons in the first place. So to start out, we're going to start with the Hamburg-Brown twist experiment. And we're going to first look at how we measure signal to noise. So what I'm showing you on the right here is some raw data that comes out of this experiment. So on the x-axis here, I have the electronic delay between these two detectors. And on the y-axis, I have how fast we get coincidences between these two detectors. Now, if we really are getting perfect biphotons into this measurement, we expect a nice strong peak at a delay of 0 nanoseconds. So the biggest contribution to this peak are actual biphotons that we wanted to measure. But unfortunately, we don't just get real coincidences. We also get these other coincidences that show up at -4 nanoseconds and +4 nanoseconds. These are noise coincidences. They come from photons that have absolutely nothing to do with each other. And in a real application, we would not be able to distinguish between these false coincidences, this noise, and these real coincidences, the signal. And the source of these false coincidences is ultimately two things. It can either be these multiphoton states, these 4, 6, and so on, or it can be the loss that we incur between the generation and the detection of these photons. So to maximize our signal to noise, one of the things we can do is we can change the pump power, which is what I've done in this plot on the right. So we're varying the pump power, and on the y-axis, we're measuring the signal to noise. And you can see that at very high pump power, we have low signal to noise. That's because we're getting a lot of this 4 state, a lot of the 6 state coming into the detector. That's creating these high noise peaks, which is lowering our SNR. As we lower this pump power, we stop getting these multiphoton states so often, and so our SNR starts to go up. Now, it eventually reaches some maximum around about 100 nanowatts, after which it declines. So the reason it declines here is because we're just not generating photon pairs anymore at such low pump powers. And so we're just losing signal altogether, and the measurement is being dominated by the electronic noise on these two detectors. And this particular noise comes in the form of what we call dark counts. It's times when the detector thought there was a photon there, when in fact there was nothing. So the other thing we can measure with this setup is something called the pair generation rate, which is how efficiently we're generating photon pairs based on how much pump power we're sending in. So on the left here, what I'm plotting is the raw count rate of each detector as we vary the pump power. And we get this nice linear behavior where when we change the pump power linearly, we see a linear change in the count rate. And now these slopes are slightly different because our detection efficiency for each detector is slightly different. But if we take this data and we combine it with the coincidence count rate, what we can work out is the pair generation rate happening on chip, which is what we're most interested in. And so for that data as well, we get this nice linear behavior between the on-chip rate and the pump power. And from here, we extract an efficiency of about 8.8 billion pairs per milliwatt. So for every milliwatt of pump I send in, I can expect 8.8 billion pairs to come out. So at this point, I want to switch to talking about why we're interested in single photons, and we'll go back to this Hamburg-Brown twist experiment again. So if I send a biphoton in here, and I see a click on this top detector I've labeled S, I know I should have a single photon in the lower detector. Now, when I plot that single photon as this probability distribution, what you'll notice is that it looks quite different. It has this negative value in the middle of it. And this is why we have to call these quasi-probability distributions, because ideally you shouldn't have a negative probability. But as it turns out, this negative part of this distribution is fundamentally important to us. If we were to build a quantum computer that only used distributions with positive states, we can show that whatever we're doing on that computer can be efficiently simulated by a classical machine. And so to gain any sort of quantum advantage, we need this negativity to happen. And this is one way we can generate it. So to quantify how well we're able to herald these single photons, we're going to do a slightly different experiment. And so the idea is, if we send biphotons into this port, what we hope is that we'll see a click on this heralding detector here. And if we see a click, then we should only have one photon in this lower part of the experiment. And so we should only see a click on either the signal detector or the idler detector, but not both. So the number that quantifies how well we're generating these single photons is this heralded G2. And the closer it is to 0, the better. If we're at 0, we have a perfect single photon that we've heralded. And as we go up, we're doing a worse and worse job of heralding single photons. So similar to the behavior for SNR, when we start off at high pump powers, we're doing a bad job of heralding single photons. Our G2 is high. And the reason that's happening is because we're getting a lot of multi-photon events. And so we're not generating true biphotons. We're generating, 3, 5, 7 photons, which we don't really want. We just want to have 1 photon. Now, as we lower the pump power, just like last time, these multi-photon events are going to become more and more rare. And it's going to lower our heralded G2 until it reaches some minimum. Now, after this minimum, if we keep decreasing the pump power, we'll start to just lose signal altogether, which will push our heralded G2 back up towards the value of 1. And so the minimum heralded G2 we get here is about 0.027, which means for every 100 single photons we tried to herald from this experiment, 3 of them were actually multiple photons. So to summarize this section, what we've demonstrated here is the first ultrafast integrated source of photon pairs with a temporal duration of just 165 femtoseconds or a maximum clock speed of 6 terahertz, far faster than what is currently on the market or in literature today. This performance we've demonstrated is also state-of-the-art at 2 micron. We achieve a total signal-to-noise ratio of about 1,000. And our performance is also on par with these other 1550 sources. So what I'm doing in this plot is I'm comparing us to all these other sources that live in the telecom band, which is much more popular. And you can see we're up here with this star. And we have some other telecom sources that beat us in pair generation rate. But that is to be expected because your generation rate becomes more efficient as you go down in wavelength. So now what I want to do is I want to flip this idea on its head. We've shown that we can generate single photons, but I want to figure out if we can detect single photons as well. So why would we want to detect single photons with something like this? What is the problem we're trying to solve? So in the last experiment, we used this kind of a detector. It's called a superconducting nanowire single photon detector. So you can see the nanowire here. It's sort of meandered back and forth in this photo. And what happens is that when a single photon hits this detector, it'll absorb some heat and it'll stop being superconducting. This will emit a pulse of electricity that we use to denote when the detector saw a single photon. Now, after some time, the detector cools down again, and it starts being superconducting again, and it's ready to detect the next photon. Now, there are 2 problems here. First of all, it's cold, and so that limits our scalability. It makes it very difficult to use outside of the lab. But second of all, this process of heating and cooling takes a finite amount of time. And for the detectors we were using, we're limited to a dead time of about 40 nanoseconds, which would place an upper bound of around megahertz on our repetition rate. Now, thankfully, this is not the only option on the market. There are detectors that work at room temperature called SPADs, or single photon amplified detectors. Now, these detectors, the way they read out single photons is they use the motion and collection of electrons. And so just like the SNSPDs, they are still limited to electronic bandwidths. And most of the detectors you can find on the market today have dead times in the tens of nanoseconds, which would limit us to megahertz of repetition rate. So the idea we're proposing here is to just use these OPAs instead to distinguish between single photons and vacuum. Because if we can get this to work, then we're only limited by the dispersion in terms of our dead time, and we can achieve dead times of less than a picosecond in this platform. So that raises the question, how do we quantify the behavior of this detector? How do we know if it can detect a single photon? So to understand how this detector works, we're going to use this equation, which is called the detector equation. Now on the left here, I have this P sub n comma rho. This answers the question, what is the probability of detecting n photons given my state was rho? This is something we can experimentally measure, and we will. Now, on the right-hand side, we have this trace operator, which is just a bit of math. But inside the trace, we have these 2 matrices. So rho is the state we're going to be measuring. It's something we're going to generate and send in to this amplifier. Pi sub n is the matrix we're actually interested in measuring. What pi sub n will do is it will quantify the quantum action of our detector and tell us how good it is at measuring these single photons. So to map that back to the setup I showed on the previous page, our input here, these are our rows, either single photon or vacuum. Our detector itself is going to be a combination of both the OPA and the photodetector that we use to read out the intensity of the pulses. And our measurement result will be a combination of the threshold and whatever came out of these detectors. And this threshold will set arbitrarily, and we'll show how their performance changes as we pick new thresholds. So the way we're going to characterize how this works is with an experiment that looks like this. So we're going to start out with our same pump. It's the old 75 femtosecond laser with a 4 nanosecond rep rate. And we're going to split it into 2 paths. Now, one of those paths will go to the top here, And it'll go into this device called an OPO, or an optical parametric oscillator. This thing I showed you earlier that was glowing green, that's actually the heart of our optical parametric oscillator. It's the OPA that lives inside the oscillator. Now, the reason we're using this OPO is because it's going to give us the same state every time. It's going to give us a state at the output that looks like this. This is what we call a coherent state. You'll notice it's very similar to the vacuum state, but it's just been shifted to the right slightly. So this is the state we're going to be using to probe the OPA. And to probe the OPA, we need to split the pump into this other path as well, so that we have some energy to amplify the state with. So in this path, we'll provide it with some time delay, so we can measure all the phases of the state. And then we'll recombine the pump and our state of interest, and we'll send them into the OPA with this objective. Now, just like last time on the output, we'll use a lens fiber to collect everything. We'll go back into free space so we can filter out the pump, so we don't measure that. We're also going to do some more bandpass filtering to remove these higher order spectral modes. And from there, we're going to do 2 measurements. So this first measurement that's happening on the OSA, this is a slow measurement that measures the average power coming out of the OPA. Now, as this stage moves back and forth, we will see this average power oscillate between amplification and deamplification and back to amplification again. And so what this curve is going to do for us is it's going to tell us the exact position of the stage when the measurement was taken. Now, on the right here, we're performing a slightly different measurement. What we're doing is we're actually resolving the amplitude of every single pulse that comes out of this chip. Now, after we measure enough pulses, we'll be able to answer the question, what is the chance I measure n photons in that pulse? And that's the information we need to reconstruct this state. So the long story short, after we process all the data, is that we can use this to detect single photons. What I'm showing you on the right here is how this behavior changes as we change the threshold. So at very low thresholds, it's easy for our detector to click. It's easy for it to measure a single photon. And so we get a higher detection efficiency of around 32%. But at the same time, it's easier for our detector to make a false click and say it saw a single photon when in fact it saw vacuum. And so our dark count probability goes up as well. Conversely, when we raise this threshold, our chances of successfully detecting a single photon go down, so our efficiency goes down to just about 26%. But our chance of having a dark count also goes down as well. Now, unfortunately, what we've shown is that this particular detector is not efficient enough to generate Wigner negativity. So we could not use this detector to perform this experiment where we generate a single photon that has useful negativity inside of it. But what you'll notice in this plot in the top right is something interesting. So this dashed line, this is how good the theory says we should do. This should be theoretically the best we can do with a perfect OPA and a perfect detection scheme. But this solid line is the experimental data. And you'll see that we're actually doing better than the theory predicts, especially at high photocurrent. So why is this? Well, the answer is something called pump depletion. So when we think about these OPAs as amplifiers, we can assign them some sort of gain, or how much that OPA amplifies its input signal. So what I'm plotting for you here is how that gain changes as we change the pump power coming into the OPA. So at low pump powers, we get very good agreement between our undepleted pump theory and the data. But at higher pump powers, our data starts to diverge, and we start to get less gain than we would expect from the undepleted pump theory. So why is this? Well, as we increase the pump power, this Chi2 process becomes more and more efficient. And so more and more of the energy from the pump is transferred into the signal. And we can sort of think of this transfer as being deterministic. So what effect does this have on our measurement? So what I'm showing you here is the following experiment, where we send in vacuum, we amplify it, and then we measure how many photons come out at the other end. And we get these probability distributions here. And so as I go across and down, I'm going up in power. We start at 87 picojoules, then we get to 135, 183, and to 222. And what you'll notice is that as we increase the pump power, the peak of this distribution starts to shift to the right, starts to shift away from 0. Despite the fact that we have not changed the input state, we're still measuring the same thing, but our measurement has become distorted by the fact that the pump is getting depleted. So the way this helps us is that when we send a single photon in there instead of vacuum, we get slightly more pump depletion, which causes this distribution to shift slightly to the right, and so it makes it a little easier to distinguish between single photon and vacuum. So if pump depletion helps us here, maybe there's a different way we can use pump depletion to get even better performance. So what I'm showing you on the left is sort of the problem we're having with detecting single photons now. These are the expected distributions for a single photon in vacuum in our current experiment, and you can see that they have a lot of overlap. And so this means that from just a single measurement, it's very hard to tell the difference between a single photon and vacuum. But if we do a slightly different version of this experiment, like this, then we can separate out these distributions. So what has changed about this experiment is a few things. So first of all, instead of our normal pump, which is actually a coherent state, we're now using a squeeze pump instead. And instead of measuring the signal at the output, what we're going to do is we're going to measure the pump, and we're going to measure the pump in a way that resolves its relative time delay to the signal. And so if we do this procedure, we will get these two distributions instead, which have very good separation, and so we can get a much higher efficiency and a much lower dark count rate. And these numbers are actually on par with SNSPDs from about 5 years ago. So if we can have this improvement to the experiment, then why aren't we doing it? Well, the answer is it's really hard. So it's very difficult to set up the homodyne detection in the first place. It's something we could do in theory, but the even more difficult part is to get the squeeze pump to happen. And that's mostly because of the losses we incur between the light outside of the chip and actually getting into the chip. If we just sent squeezed light through that, we would lose everything to how much loss we have. But the other more fundamental reason that we don't do this is because it requires G over K to be greater than 1. So this is one of the problems I introduced at the beginning. This is the place where it's limiting us. It's preventing us from doing this better measurement that would allow us to better distinguish between single photon and vacuum. So what we've shown throughout this section of the talk is the first demonstration of a room temperature nanophotonic single photon detector with a dead time of just 75 femtoseconds, which would limit us to a repetition rate of about 13 terahertz. Now, unfortunately, our efficiency isn't very high compared to conventional detectors. And to quantify that in the context of the last source, our maximum SNR is about 4 here, even if we had a perfect source and no loss between the source and the detector. Whereas with the previous source, when we were using this OPA as a source instead, we got an SNR of 1,000. And that was with a loss of 99% between the source and the detector. But what we've also shown is that this is not the end of the road, and that if we can solve this G over K problem, we can use this in a regime where it becomes experimentally useful for us. So now what we're going to do is we're going to take a slightly different approach to detection. Instead of just looking at one pulse that comes out of the amplifier and trying to use that to determine if we saw a single photon or vacuum, we're going to look at many pulses that come out of the amplifier. And we're going to use the statistical information we build up from those pulses to actually reconstruct a full description of the quantum state at the input of this amplifier. So the problem we're trying to solve here is something called homodyne detection. This is what I wanted to do with the pump a couple slides ago. And what homodyne detection does is it gives us some information about the phase of the light coming in. And if we take enough homodyne measurements, we can fully reconstruct the quantum state we're trying to measure. Now, the problem with using homodyne detectors is that they're electronics, right? And so we're limited to this electronic bandwidth. We can't really get beyond 100 gigahertz. So to overcome this problem, we can use OPAs as homodyne detectors in their own right. And we can do this because they use phase-sensitive amplification. So we can still recover some of that phase information. And the idea is very similar to the last detector, where we amplified this state, we measure all the statistics that come out of it, and from those statistics, we can reconstruct a full description of the state, which I'm showing you here. Okay, so how does this work? So we start out with a single OPA, and we're going to send in a pump and some vacuum. And after that OPA, we're going to get squeezed vacuum again. So this is the state we're actually going to be trying to measure here, this squeezed vacuum. So to measure it, we're going to introduce a second pump. It's going to have some time delay between it and the first pump, so we can measure all the phases of this state. And then we're going to send them to a device that looks like this. So what I'm showing you here is called a coupler. And the idea is that when we bring these black lines together, these waveguides where the light is traveling, we can bring them so close that that light at the signal wavelength can actually jump that gap and end up in this top waveguide. Now, conveniently, this pump light, since it's at half the wavelength, it has much tighter confinement to that waveguide, and so it will not be able to cross over this gap. So this lets us get rid of this old pump that we use to generate the squeeze vacuum and introduce this new pump, which we will use to measure the squeeze vacuum. So from here, we go into a second OPA where we amplify the squeeze vacuum. And when we amplify it along its anti-squeeze portion or along this x-axis, we're going to wind up with this blue distribution that's very spread out in photon number. And when we amplify it along its squeezed axis, we're going to end up with this red distribution, which is sort of compressed towards 0. And then this black distribution here, this is our vacuum reference. This is what happens when we block this lower pump from coming in, and we just let this amplifier measure the vacuum state. Now, what I've described up to this point is an experiment we already did back in 2022. And what we did in this experiment is we showed that by using these OPAs as measurement devices, we can measure record levels of squeezing on chip. And I'm showing that here in the plot on the bottom right. So this is our work. So we're winning both in bandwidth, which is going to help us go fast, and also in measured squeezing. And generally, the more measured squeezing, the better, the more useful things we can do with it. Now, our contribution here was to actually take the measurement device and put it on chip. As I mentioned earlier, part of the challenge with using squeeze light is loss. If you want to measure squeeze light or any quantum state, really, and you lose most of it by the time you get to the detector, then you're just going to measure noise. And so to overcome that problem, we just take the detector and we put it on chip so that we don't have to deal with any of these losses from going off chip. So what we want to do now is we want to take this a step further. Instead of just recovering the average squeezing and anti-squeezing, this is what I'm showing here. This black curve is what happens as we allow the two pumps to oscillate and walk off of each other. We measure first anti-squeezing and then squeezing, back to anti-squeezing. What we want to do now is we want to recover more information from the state. We actually want to do a total reconstruction of this probability distribution of the state we had at the input. So to do this, we're going to do one more thing at the output. And that's use this photodetector here. And what that's going to do is it's going to measure the amplitude of every single pulse. That will allow us to build up the statistics we need to work out what this state was at the input. So similar to the last experiment, so this is the experimental setup we're going to use to measure this. Very similar to the last experiment. We start out with our mode lock laser again, and we break it into two paths. We're going to time delay one of those paths so that we measure all the phases. And then we're just going to recombine both beams and send them into the chip. So in the lower OPA here, we're going to generate our squeeze vacuum with the first beam, and then we're going to measure it with the second beam in the second OPA. At the output of this chip, we're going to collect all of the light with our lens fiber. And we're going to send it back into free space so we can get rid of the pump and do some bandpass filtering to remove higher order spectral modes. At the measurement phase, we're going to take the exact same measurements we took last time. We're going to use this slow measurement to determine the exact time delay of this stage. And we're going to use this fast measurement to get the statistical information. So this is what the raw data looks like coming out of this experiment. What I've plotted here are some photon number distributions for different measurement phases, or equivalently different time delays between the two pumps. And what we're going to do is we're going to take this data and we're going to feed it into an algorithm that uses that same equation, except now we know the term on the left still. We're going to assume we know what pi sub n is. We're going to assume we know what the action of the detector is. And we're going to say that our unknown is rho, and we're going to try and reconstruct rho. So we would feed all this raw data into this algorithm. This algorithm, called the maximum likelihood algorithm, would find the rho that is most likely to have produced our measurement results. Now, there are two problems with this data with the way that it stands. And the first problem is that it doesn't peak at 0. So we know that for squeezed vacuum, our photon number distribution should peak at 0. And so if we took this data and fed it into that algorithm blindly, what we would get is a distribution with a big hole in the middle of it. And we know that's not true. That's not actually what we're trying to measure. So we have to fix that problem somehow. So the other problem we have to fix is that we have multi-mode contributions as well. So because our amplifier has this extremely broad bandwidth, it actually amplifies lots and lots of different things at the same time, most of which we're not actually interested in measuring. We just want to measure the fundamental mode. And so we'll have to come up with a strategy to separate out contributions from higher order modes and focus on just the fundamental mode. So the strategy we're going to use is we're going to model this distribution and then we're going to fit it. So we know that for a squeeze vacuum, we should have a distribution that looks like this. It's this exponential weighted by this 1 over the square root of x term. Now, we know from other parts of this experiment that what we're looking at the detector has an average mode number of 1.35. So we really just have most contributions from one mode and some smaller contributions from that second order mode. And so to quantify what these distributions look like, we're just going to generate a distribution up to 2 orders, like I'm showing here. Now, the way to think about this intuitively is we need to add up all of the probabilities that result in the same measurement outcome. If I measure 3 photons, I need to add up the probability that 2 of them came from mode 1 and 1 of them came from mode 2, and vice versa. And the way we'll add up those probabilities is with this integral here. So when we calculate these distributions and we try and fit them to the data, we get a reasonably good fit. We're able to fit all of the distributions we measure. And by fitting these distributions, we can recover the squeezing in the fundamental mode and isolate ourselves from those higher order modes. Now, the way the offset problem is dealt with is we just let our photon number have some free offset that it finds as it fits these distributions. And so we get a nice looking fit for everything that we measure. So from here, we have the squeezing in the fundamental mode for all the phases. And what we'll do is we'll take these distributions, feed them back into our measurement algorithm, and see what comes out. So in the top left here, I'm showing you the expected rho. So rho is some matrix. I'm just plotting the numbers here. It's not important what the matrix itself looks like. But what is important is what our recovered rho looks like. And thankfully, it looks basically exactly the same as this matrix we generated up here. So this is what we expect for a perfect squeeze state. This is what we get from feeding the fitted data in to our algorithm. And this is the difference between them. So the difference is very, very small. This is a sanity check to make sure that our data processing is working and we're actually recovering something we expect. And then on the right here, I've turned this rho into a probability distribution again, which is all the same information. It's just a way to present it visually that makes a little more sense. Now, if we had better detection efficiency and better filtering, we would actually not need this technique of fitting the data. If we could have those things, this algorithm would work for any arbitrary quantum state, and would also work up to 6 terahertz, which is the dispersion limit of this particular amplifier. So to summarize what I've shown you, what we're looking at here are the building blocks of an ultrafast quantum computer. It's not a full-scale system yet. Nothing I have shown you here will actually do anything useful or anything that will make you money. And so the next step we need to take is to put a bunch of these devices together to actually get a circuit that can do something for us. So thankfully, we already have a roadmap to go off of, and that's electronics. So what I'm showing you on the left is the first integrated transistor from 1958. And on its own, this transistor probably isn't useful. It probably doesn't even have better metrics than bulk transistors. But over the last 60 years, we've figured out how to take a bunch of these transistors and put them onto a single chip, billions of them on a single chip. And by coming together in this large-scale platform, we can actually use these transistors to do something useful. So we're currently at the same place with nonlinear optics. We've demonstrated our ultrafast OPAs. We've demonstrated that they work. They can generate and measure states. Now it's time for us to put everything together into one large platform to realize a useful quantum computer. So what's stopping us from doing this? Well, the first thing that's stopping us is fabrication. As it turns out, it's very difficult to fabricate these devices, and it's difficult to fabricate them in a way that they have very low loss. So there are some solutions to this problem, and one of them is this technique called atomic layer etching, in which we just remove one layer of the lithium niobate at a time, which gives us a much smoother sidewall, which can greatly improve our losses. Now, the other problem we face during fabrication is thickness variation in our chips. So we buy these chips in the form of a large wafer from a commercial company. And when that wafer shows up, it has a thickness variation that looks like this. So we get about 8 nanometers of variation across the 20 centimeter wafer. Now, that might not sound like much, but that's more than enough to throw off the phase matching of our devices and cause them to stop working. But thankfully now we have metrology tools that are sophisticated enough to map out these local variations in thickness, and so we can just adjust our design to compensate. So if we can get these two things to work together, if we can get the losses to be low and our devices to be reliable, then we can eventually solve the problem I introduced at the beginning, which is the nonlinearity. So what this nonlinearity is doing for us, because it's low, is it's limiting the pump signal entanglement. It's preventing us from doing measurements on the pump, which can tell us something about the signal. And as I mentioned earlier, these techniques are very powerful and can lead to a huge increase in performance for us. But we're not there yet. So one of the ways we can fix this is by lowering K, lowering this loss. And the idea is that if we can lower K and we can raise G somehow, then we can eventually realize these ultra-fast, all-optical quantum computers in a chip-scale, room temperature platform. So that concludes the technical portion of my talk, and I have this gigantic list of publications here. But first, I'd like to go to the acknowledgements slide. And of course, the first acknowledgement I'll give out is to my advisor, Alireza Morandi, who was very kind to take me into his lab as a summer student who was messing around with FPGAs, and very kind to spend 30 grand and then do it again for some reason. And I've really enjoyed working with Alireza. He's taught me a lot about how to do research and how to be a better scientist, and that has had a huge impact on me, so thank you. So next, I would like to thank all of the members of my committee, Professor Kerry Valhalla, my chair, Professor Actual Chair, who's joining us on Zoom, and Professor Mohammed Mir Hosseini. I'd like to thank you all for all of the technical and professional advice that you've given me. It's been hugely impactful. And as I was writing up my thesis, I often found myself referring to the notes I took in your classes. So thank you. So next, I'd like to thank Alina Sendinaris, who's somewhere here. Hi. You probably saw her name on some of the previous slides. We worked very closely together to make these projects work, and she was an invaluable addition to that. She came up with all of the theory we needed to understand what exactly was going on in these OPAs. Next, I'd like to thank Gordon Lee, who is my roommate, lab mate, office mate, and I think most prolific collaborator based on number of papers. He's always been very supportive of the work that we're doing and always brings up interesting questions about what exactly are the applications and how we can improve them. I'd like to also thank Thomas Zacharias. He is the person who's helping us continue the quantum effort after I'm gone and improving our measurement techniques. I'd also like to thank Christian Leifmans. He's a former student of the group who was my surf mentor when I initially joined the group. And he very much made me feel welcome and took the time to explain everything that was happening in the experiment. That was very kind of him. So of course, I would like to thank the entire Nonlinear Photonics lab, as well as some other former and current members. So Rajveer Nehra, who's now a professor at UMass Amherst, he started the quantum effort in our group, and he put us on the path to success for these projects. Dr. Media Parto, who's now a professor at Creole in Florida, also gave us lots of technical advice that went into making these things work. I'd also like to thank Robert Gray, Ryoto Sakine, and Luis Ledesma for all of the both fabrication and experimental help you've given me and the other quantum people throughout this journey. And of course, I'd also like to thank all of my family members who are here today. They have been endlessly supportive of me throughout this journey, both emotionally and materially, and I very much appreciate that. I could not have done this PhD without them. But of course, no acknowledgement section of mine would be complete without mentioning the most important thing I did at Caltech, outside of research, of course. And that's the union. So when I initially got to Caltech, it was clear that there were serious problems and that nothing was really being done to address them. But at some point, we banded together and we decided to do something about it. And that thing we did was we formed our union. And through forming that union, we've been able to make serious improvements to the lives of students and postdocs here at Caltech. We've won better wages, better time off, better vacation policies, funds for international students to renew their visas, real protections from harassment and abuse. Okay, this is the last slide. So, but most importantly of all, what we've established is a way for the students to advocate for change they want to see in their workplace. And so I'm very much proud and honored to have taken part in this piece of Caltech's history with you all. And I'm confident that the union that we have built together will continue for a long time and continue to improve the lives of graduate students and postdocs. But the most important lesson I learned throughout this journey, and the lesson I leave you all with today, is that when it comes to protecting your rights, the best defense is often a good offense. So with that, I will conclude my presentation, and I'm happy to take any questions.